Hi everyone, we are Group 24 and my name is Hongpei Lu. Our research will focus on the topic of Cipher suit evaluation in the given experimental track section. Nowadays, Cipher suits are implemented widely in the network to secure communication, and it is important to select an appropriate Cipher suit. As there are many dimensions to evaluate the Cipher suits, such as security, performance, and compatibility. Our research will mainly focus on the performance evaluation for the Cipher suits. We will design and implement an experiment to evaluate the performance of the encryption part in the Cipher suits. Different factors such as Cipher modes, algorithms, key length will be modified to investigate the effect of processing speed. The results will be discussed in the research. First, I will introduce some basic concepts, and my group member He-Qing will introduce the algorithms and the methodology part. The Cipher suit is a set of algorithms and protocols adopted to secure communication. It consists of 4 parts as shown in the picture. Key exchange is used to exchange symmetric keys such as DH and RSA. The authentication part is implemented between clients and servers, but it is not a necessary condition as the identity cannot be authenticated. Encryption is the algorithm to encrypt the data, and the hash or MAC function is the algorithm to check the data integrity. In our research, we will focus on the performance in the encryption part by measuring algorithm speed. One of the variables in the experiment is the block cipher mode, which is a technique used to enhance the algorithm effect for the application. And there are 5 modes defined by NEST, which are ECB, CBC, CFB, OFB, and CTR. Considering the security level, the ECB mode will not be tested, and the research will mainly focus on the CBC, CFB, and OFB mode, as the CTR is not supported by some algorithms we selected. CBC can be used in authentication and general-purpose block-oriented transmission. The encryption import will XOR plain text block and the preceding cipher text block. CFB can also be used in authentication and general-purpose stream-oriented transmission. The preceding cipher text is used as input to the encryption algorithm to produce output and XORed with the plain text to produce the next unit of ciphertext. OFB is similar to the CFB mode, but can be used for stream-oriented transmission over a noisy channel. The preceding encrypting output is the input to the algorithms and the full blocks are used. And next, He-Qing will introduce the algorithms part.
So there are a few algorithms which we are going to explore their performance. We have chosen some common ciphers such as DS, AES, Kalemia, and CAST in our experiment. In this section, I'm going to briefly go through each of them. The first one is data encryption standard, also known as DES. It was a very common symmetric encryption algorithm. The graph on the right is a DES in 5-step structures. We have seen it in the lecture. The key length of DES is 56 bits, which results in 2 times 56 possible values. It was considerably secure. Breaking such cipher was dramatically expensive and impractical in the past. However, with the growing capabilities of hardware, current technologies makes the DS much more vulnerable under the brute force attacks. But we're still going to evaluate its performance for the purpose of comparison as a baseline. The next one is advanced encryption standard. It is one of the algorithms that takes the place of the DS. One main update here is the length of the key. It was raised from 56 bits to 128 bits, 192 bits, or to 56 bits. During the encryption process, the plaintext and keys are both decrypted in the 4x4 matrix, which is known as a state array, and it is modified in each stage. Moreover, the key is also expanded, which will be used in multiple rounds. The number of rounds is dependent on the length of the key. And the Camellia is a modern cipher with a high security level. It accepts the key letters of 128, 192, and 256, just like the AES. And the Camellia is based on a 5-step structure with 18 rounds in total. In every 6 rounds, logical functions called FL and the inverse of L are inserted to widen to the input and output. During the encryption, the plaintext is firstly XORed with 2 subkeys, which are KW1 and KW2, then separated in 2 parts and perform the operation on the left side, which you can see over here. This is for rounds 1 to 18. For the rounds 6 and 12, it performs the following operation over here. At the end of the process, the algorithm outputs a 128-bit ciphertext. And the last one is cost algorithm. It is what we chosen here is the cost 128, which is also known as cost 5. It is also based on a 5-step network with 12 or 16 rounds. Key lengths vary from 60 to 128 bits. It involves various components, as you can see in these pictures. S boxes are based on band functions with a size of 8 times 32 bits. Other operations such as key-dependent rotations, modular addition, subtraction, and XOR operations are also included. In each round, they can apply XOR, modular addition, and subtraction in different orders.
To evaluate the different bulk encryption, we will use OpenSSL to perform experiments on different cipher suites. The parameter for block cipher performance is bytes per second processed. We set 3 variables. The first one is a combination of different block cipher algorithm and block cipher modes. The second one is key length, and the third one is block size. Algorithms will cover AES, DES, Camellia, and CAST. Block cipher modes will cover CBC, CFB, and OFB. Key length varies from 64 to 256 bits, and the block size varies from 16 to 8,192 bytes. Because the performance depends on the hardware, and some of the block cipher algorithms are hardware accelerated, we will also record the hardware used to run the tests. The tool we use to benchmark and evaluate the cipher suites is OpenSSL. It is an open-source security library as well as a command line tool. OpenSSL provides implementation of SSL and TSL protocols, which includes the cipher suites we need to test. It is written in C and supports a wide range of operating systems. It is also widely used by internet servers, including the majority of HTTPS. Therefore, testing and benchmarking using OpenSSL is handy and practical. The latest version of OpenSSL is 3.0, which includes the 3 variables as built-in block ciphers. Here's a snapshot of some of the supported ciphers. As you can see, the key length and the block cipher modes are embedded in the ciphers. For example, the AES 192 OFB is AES algorithm with a key length of 192 bits and runs in output feedback mode. We will run different ciphers with control variables, like shown in the graph. The third variable block size is included in the speed command. The speed module of the OpenSSL command line tool can benchmark all the built-in ciphers. Every run of a cipher includes several different block sizes, from 16 bytes, 64 bytes, up to 16,384 bytes. The screenshot is the output of running this command. The EVP option allows OpenSSL to use EVP interface, which has an extensive range of algorithms and external hardware crypto supports. Second, specify the time to run encryption for each block size. Elapsed option will set the measurement in wall clock time rather than CPU user time. Here are the references we used in this presentation. Thank you for listening.